The thermometer outside Dietrich Stoltzfus's elevated cabin read -52 degrees Fahrenheit, yet inside he sat comfortably in his shirt sleeves while a modest fire burned in the stone hearth. 300 yards down the valley, Wilhelm Brenner huddled in his ground-level cabin wearing every piece of clothing he owned, feeding log after log into a roaring fire that barely kept the interior above freezing, and the engineering principle that made the difference would transform mountain survival across the entire northern Rockies. Before we continue, let us know where you're watching from, and if stories of frontier innovation move you, hit that subscribe button, because tomorrow's episode reveals an even more unbelievable survival technique that saved lives during the harshest winter on record. The winter of 1836 arrived early in the northern Rocky Mountains and settled in with a cruelty that shocked even veteran trappers. By mid-November, temperatures had dropped to -30 degrees and stayed there for weeks. By December, -40 became routine. Men who had survived a decade in the wilderness began losing fingers and toes to frostbite while sitting inside their own cabins. The paradox was maddening and inescapable. A man could tend a fire all night, burning through half a cord of split wood, and still wake to find ice crystallized on the interior walls and his water bucket frozen solid 3 feet from the hearth. Dietrich Stoltzfus had spent 4 winters in the mountains trapping beaver along the tributaries that fed the Yellowstone River. He was methodical, cautious, and technically minded in ways that set him apart from most mountain men. His father had been a carpenter in Pennsylvania, and Dietrich had absorbed principles of construction and engineering before heading west at age 23. He understood joinery, load distribution, and thermal properties of different materials. But even with that knowledge, the winter of 1836 tested him in ways he hadn't anticipated. He shared a cabin that season with Heinrich Vogel, a German immigrant who had come to the mountains 3 years earlier. Their structure was typical of the era: logs notched at the corners, mud and moss chinked between gaps, a single door, 2 small windows covered with oiled paper, and a stone fireplace that Heinrich had built with surprising skill. The cabin sat in a small clearing near a creek, positioned for convenient water access and proximity to beaver ponds. They had selected the site using the same logic every trapper used: practical considerations of daily survival. The cold that winter revealed something Dietrich had never fully understood. Heat didn't just escape through gaps in the walls or up the chimney, it was being stolen from below, pulled down through the floorboards into the frozen earth beneath the cabin. He first noticed it in mid-December when he dropped a metal cup on the floor and watched it frost over within minutes. The floor itself felt like ice, despite the fire roaring 8 feet away. He began paying attention to temperature gradients inside the cabin. At ceiling height, the air was warm enough to be comfortable. At waist height, it was tolerable. At floor level, it was brutally cold. He mentioned this to Heinrich one evening as they sat near the fire. Heinrich shrugged. "Ground is frozen. Nothing to be done about it." It was the same acceptance Dietrich heard from every trapper he spoke with. The earth was cold in winter. Cabins were built on the ground. Therefore, cabin floors were cold. The logic seemed ironclad, and the conclusion seemed inevitable. But Dietrich couldn't stop thinking about it. The heat loss through the floor wasn't minor, it was catastrophic. They were heating the entire mass of frozen earth beneath their cabin, a thermal sink that extended hundreds of feet down into the mountain bedrock. On January 14, 1837, the temperature dropped to -58 degrees. Dietrich and Heinrich had prepared as well as any men could. They had split and stacked 4 cords of firewood within arm's reach of the cabin door. They had sealed every visible gap in the chinking with fresh mud mixed with animal hair. They had hung blankets over the windows as additional insulation. They kept the fire burning continuously, feeding it every 2 hours throughout the night. Heinrich took the first watch that evening, tending the fire until midnight, while Dietrich slept under every fur and blanket they owned. At midnight, they switched. Dietrich fed the fire and watched the flames consume log after log, generating heat that seemed to vanish into the floor and walls faster than it could warm the air. He could see his breath despite sitting 4 feet from the hearth. The stone fireplace radiated heat, but it felt like trying to warm an endless cave with a single candle. At 4 in the morning, Dietrich added 3 large logs to the fire and returned to his sleeping platform. Heinrich was motionless under his pile of furs, but that wasn't unusual. Men slept deeply after exhausting days in the cold. Dietrich pulled his own blankets tight and drifted into fitful sleep, waking periodically to check the fire's status through half-open eyes. When dawn light finally penetrated the oiled paper windows, Dietrich rose and immediately added wood to the fire, which had burned down to coals. He heated water for coffee and called to Heinrich. No response. He called again, louder. Still nothing. He crossed to Heinrich's sleeping platform and pulled back the furs. Heinrich Vogel was dead. His body was rigid, frozen in the position he had assumed when lying down to sleep. His face was peaceful, showing no signs of struggle or awareness. He had simply gone to sleep and never woken up. The cold had taken him quietly while Dietrich slept 8 feet away, and a fire burned in the hearth between them. Dietrich stood motionless, for several minutes trying to process what had happened. Heinrich was 34 years old, healthy, experienced in winter survival. He had dressed properly, used adequate bedding, and slept in a cabin with an active fire. By every standard of frontier logic, he should have survived the night. But the temperature beneath his sleeping platform, measured later that morning with a thermometer Dietrich kept for tracking weather, registered -12 degrees. The air at ceiling height was 42 degrees. The fire had heated the upper cabin adequately, but the cold radiating up from the frozen earth had created a lethal zone at floor level where Heinrich slept. Dietrich realized with absolute clarity that he could have been the one who died. The only reason he survived was random chance. His sleeping platform happened to be positioned slightly higher and closer to the fireplace. The cabin hadn't failed. The fire hadn't failed. The fundamental design of ground-level construction had failed, and if it could kill Heinrich, it could kill anyone. The ground was frozen 18 inches deep. Dietrich spent 2 days breaking through the iron-hard earth with a pickaxe to create a grave on the hillside overlooking the creek where Heinrich had run his trap lines. The physical labor was brutal, but it gave him something to focus on besides the reality of what had happened. He wrapped Heinrich's body in canvas and buried him with what little ceremony seemed appropriate for a man who had died alone in the wilderness. After filling the grave and marking it with stacked stones, Dietrich returned to the cabin and began a systematic examination of its construction. He wasn't looking for defects in workmanship. The cabin was solidly built by frontier standards. He was looking for the mechanism of heat loss that had killed his partner. He started with the floor. The floorboards were split logs, hewn flat on one side and laid across support beams. Beneath the floorboards was approximately 8 inches of airspace, then bare earth. The earth was frozen solid, and that frozen mass extended down into the bedrock. Dietrich placed his hand on the floorboards and felt cold radiating up through the wood. He lit a candle and placed it on the floor. Within 10 minutes, the wax around the base had hardened noticeably despite the ambient air temperature being above freezing near the fire. He moved his examination to other cabins in the area. Over the next week, he visited 4 neighboring trappers and asked permission to examine their floor construction. Every cabin showed the same design: floorboards laid on beams, minimal air gap, direct proximity to frozen ground. Every cabin had the same problem. Heat generated inside was being conducted down through the floor into the infinite thermal mass of the frozen earth. He spoke with old-timers who had survived 20 winters in the mountains. They acknowledged that floors were cold, but considered it an unavoidable reality. "Can't build a cabin in the air," one grizzled trapper named Wilhelm Brenner told him. "Got to set it on something, and that something is the ground. You want warm feet? Wear better boots." The logic seemed unassailable. Every structure required foundation. Foundation meant contact with earth. In winter, earth was frozen, therefore structures would be cold at floor level. It was simply how things worked. But Dietrich couldn't accept that conclusion. He had seen Heinrich freeze to death 8 feet from an active fire because cold from below overwhelmed heat from the hearth. That wasn't an acceptable trade-off. That wasn't survival. It was slow-motion disaster waiting for the right combination of temperature and bad luck. There had to be a solution, something that would interrupt the thermal connection between cabin floor and frozen ground. He began sketching ideas in a journal, working through possibilities during the long evenings alone in the cabin that now felt like a death trap. Spring arrived late in 1837, and with it came the seasonal migration of trappers heading to trading posts to sell their winter's work. Dietrich packed his furs, a modest catch since Heinrich's death had forced him to work half as many trap lines, and joined a group of 5 men traveling to Fort Union on the Missouri River. The journey took 3 weeks on horseback, following established trails through mountain passes still choked with late-season snow. During the travel, Dietrich listened to the other trappers discuss the winter. 2 men had lost toes to frostbite. Another had abandoned his cabin in February and moved in with a partner because he couldn't keep his structure warm enough to survive alone. Every man had burned through more firewood than any previous winter. They spoke about the cold with a mixture of pride and resignation, as if surviving extreme conditions was a test of character rather than a problem that might have solutions. Dietrich asked questions. How thick were their cabin walls? What materials did they use for chinking? How large were their fireplaces? Did they notice temperature differences at various heights inside their cabins? Most men hadn't thought about these details. Their cabins were built using techniques passed down from other trappers or remembered from childhood homes in Kentucky, Pennsylvania, or Ohio. The methods worked adequately most winters, so there was no reason to change them. But adequately wasn't enough anymore. Dietrich had watched a healthy man freeze to death in a properly built cabin with an active fire. That reality gnawed at him throughout the journey. At Fort Union, while other trappers spent their earnings on whiskey and supplies, Dietrich spent 3 days observing how the trading post's permanent structures were built. The fort's main buildings sat on stone foundations that elevated the floor beams 6 to 8 inches above ground level. The gap was minimal, but it existed. He asked the fort's carpenter why they bothered with stone foundations instead of setting beams directly on the earth. The carpenter looked at him as if the question was stupid. Moisture, the man said. Ground moisture rots wood. You set beams on bare earth, they'll be rotted through in 5 years. Stone keeps them dry. Dietrich asked if the gap also affected temperature. The carpenter shrugged. Maybe some. Mostly it's about moisture. But Dietrich's mind was racing. If 6 inches of air gap prevented moisture damage, what would 6 feet of air gap do for thermal isolation? The idea seemed absurd on its surface. Building a cabin suspended well above the ground defied common sense and would require engineering far beyond typical frontier construction. But absurd didn't mean impossible. Dietrich remained at Fort Union for 2 additional weeks after selling his furs, studying structures with an intensity that made other trappers think he had lost his mind. He wasn't interested in the fort's defensive walls or living quarters. He was obsessed with the elevated storage buildings positioned at the edge of the compound. These structures stood 8 to 10 feet off the ground on thick timber posts, designed to keep grain and supplies away from ground moisture and rodents. He spent hours examining how the posts were set, how the floor beams connected to the posts, and how weight was distributed across the support system. The structures held thousands of pounds of grain without sagging or shifting. The engineering was simple but effective, vertical posts bearing vertical loads, with cross-bracing to prevent lateral movement. The elevation kept the stored grain dry even during spring floods, when the Missouri River rose and saturated the surrounding ground. Dietrich sketched the construction details in his journal, noting post spacing, beam dimensions, and connection methods. He measured the gap between ground and floor, calculated the weight capacity based on visible grain storage, and examined how the structures had weathered over multiple years. The elevated design worked perfectly for its intended purpose. But could the same principle be adapted to create a livable cabin that would stay warm in extreme cold? The thermal advantage seemed obvious. 8 feet of air between cabin floor and frozen ground would eliminate direct heat conduction. Cold air would circulate beneath the structure rather than conducting heat away through solid contact. The cabin would essentially float in space, thermally isolated from the earth that had killed Heinrich. But the engineering challenges were substantial. A storage building didn't need to be weatherproof or insulated. It didn't require a heavy stone chimney or accommodations for human habitation. It just needed to keep grain off the ground. A cabin was different. The structure would need solid walls capable of withstanding winter storms. It would need a functional fireplace and chimney system, adding significant weight to one side. It would need windows, a door, and interior space comfortable for extended occupation. Most critically, it would need to remain stable during high winds and heavy snow loads. An elevated platform that worked for storing grain might collapse under the lateral forces of a mountain storm hitting a fully enclosed structure. Dietrich sought out the fort's head carpenter, a Norwegian immigrant named Gustav Thorsen, who had built most of the permanent structures. He explained what he was considering: a full-sized cabin elevated 8 feet above ground on a timber support system. Gustav listened, then asked practical questions. What would the total weight be? How would the support posts be anchored? How would lateral forces be managed? What about access and security? They spent an afternoon working through the engineering problems. Gustav sketched alternative support configurations, explaining why vertical posts alone wouldn't work for a cabin-sized structure. The wind load would create too much lateral force. Dietrich would need diagonal bracing or an entirely different support geometry. Gustav suggested a cantilever system, a large beam running perpendicular to the cabin with angled supports creating triangular bracing. The geometry would convert lateral forces into compression forces along the angled supports. Dietrich returned to the mountains in early July 1837 with supplies that baffled every trapper who saw them. He had purchased 3 massive timbers, each 16 feet long and 20 inches in diameter, that had been milled at Fort Union from cottonwood trees. Transporting them required 2 pack mules and consumed most of his fur trade profits. He also carried iron brackets, heavy bolts, a specialized crosscut saw, and a detailed set of drawings Gustav had helped him create. Wilhelm Brenner encountered Dietrich on the trail 15 miles from the trappers' scattered camps. Wilhelm was heading to Fort Union with his spring catch while Dietrich was returning. They stopped to share coffee and exchange news. Wilhelm examined Dietrich's unusual cargo with undisguised skepticism. "What are you building, Stoltzfus? A bridge?" Dietrich explained his plan: a cabin elevated 8 feet above ground to eliminate heat loss through floor contact with frozen earth. Wilhelm stared at him for a long moment, then laughed. "You're going to build a cabin in a tree, like a child's fort?" Dietrich explained the engineering principles: thermal isolation, cantilever, support geometry, load distribution across triangular bracing. Wilhelm's amusement only increased. "Heinrich's death scrambled your brain. A cabin sits on the ground. That's how cabins work. You can't just—" He gestured at the massive timbers. "Stick a house up on poles like a grain shed. First wind will knock it over. First bear will push it down. You'll freeze to death in the wreckage come winter." Word of Dietrich's plan spread through the small trapping community. Within days, men who hadn't spoken to him since Heinrich's death suddenly appeared at his campsite to examine his materials and question his sanity. A trapper named Rudolf Kern suggested Dietrich was suffering from grief-induced madness. Another man, Otto Lindemann, was more diplomatic but equally skeptical. "I understand wanting to solve the cold floor problem," Otto said, "but this seems complicated. Why not just build thicker floors, more insulation beneath the boards? Dietrich had considered that approach. He explained that insulation would slow heat loss, but not eliminate it. As long as floor and ground maintained physical contact, heat would conduct away. The only solution was complete separation, an air gap large enough to interrupt thermal transfer entirely. Otto nodded slowly but didn't seem convinced. Well, good luck. Hope you finish before snow flies. The mockery intensified when Dietrich began clearing his construction site. He chose a location on a slight rise 300 yards from the creek where Heinrich was buried. The elevation provided drainage and visibility, but made water access less convenient. Wilhelm Brenner stopped by during the clearing work and openly questioned the site selection. "You're building uphill from water? Going to haul every bucket 300 yards? For a cabin that'll probably collapse before Christmas?" Other trappers adopted the derisive nickname Wilhelm coined, Stoltzfus's folly. Some called it the floating cabin or the treehouse. None expected it to work. Construction began in late July 1837 with preparation of the primary support beam. Dietrich selected the largest of his 3 purchased timbers, a cottonwood log 18 feet long and 22 inches in diameter at its narrowest point. Cottonwood wasn't ideal for structural work. Pine or oak would have been stronger. But cottonwood was available in the sizes he needed and weighed less than denser woods, making transport possible. He spent 4 days stripping bark and shaping the beam to consistent dimensions using a draw knife. The work was back-breaking. Each pass of the blade removed thin strips of wood, and he needed to remove irregularities along the entire 18-foot length. But consistency was critical. The beam would bear the cabin's entire weight, and any weak points or irregular grain could cause failure. He worked slowly, examining the wood grain for knots or defects that might compromise structural integrity. Once the primary beam was prepared, Dietrich dug the foundation holes. The beam would rest on 2 stone piers positioned 14 feet apart, creating a balanced platform with 2 feet of beam extending beyond each pier. The piers themselves required careful construction. He excavated holes 3 feet deep, then filled them with layers of flat stones mortared together with mud and lime. Each pier rose 18 inches above ground level, providing drainage and preventing direct earth contact that could cause rot. The angled support beams presented the next challenge. According to Gustav's drawings, these would connect from the ends of the primary beam up to the cabin's underside at approximately 45-degree angles, creating triangular geometry. Dietrich shaped the 2 remaining cottonwood timbers into support beams 14 feet long. The angle calculation was critical. Too steep, and the beams would bear excessive compression forces. Too shallow, and they wouldn't effectively brace the structure. He created connection points using a technique Gustav had detailed: mortise and tenon joints reinforced with iron brackets. At the base, each angled beam would slot into a carved mortise in the primary beam's end. At the top, the beams would connect to iron brackets mounted to the cabin's floor frame. The joints had to be precise. A loose connection would allow movement and eventual structural failure. By mid-August, the foundation system was assembled on the ground for test fitting. The primary beam rested on its stone piers, and the angled supports were positioned to verify angles and connections. Dietrich examined every joint, every measurement, every connection point. The system looked absurd, a giant triangular structure sitting on a hillside, connected to nothing, supporting nothing. Several trappers stopped by to observe the strange framework. Wilhelm Brenner shook his head. "That's supposed to hold up an entire cabin? Through winter storms and snow loads? Stoltzfus, you're wasting your time and good timber." But the geometry was sound. The mathematics Gustav had worked out confirmed it. The triangular bracing would convert the cabin's weight and any lateral forces into compression along the angled beams. As long as the wood held and the connections remained solid, the system would work. With the foundation system prepared, Dietrich faced the most daunting challenge, constructing cabin walls 8 feet above ground level. Traditional cabin building relied on stacking logs directly on a foundation, with each course supporting the next as the walls rose. But Dietrich's design required building the entire floor frame first, mounting it on the cantilever supports, then constructing walls on an elevated, potentially unstable platform. He began with the floor frame, assembling it on the ground as a complete unit. He used logs 10 inches in diameter, notched and fitted into a rectangular frame 12 feet wide by 20 feet long. Across this frame, he laid floor joists, smaller logs 8 inches in diameter, spaced 18 inches apart. The joists would support the floorboards and distribute weight across the frame's perimeter. He connected everything with iron brackets and wooden pegs, creating a rigid structure that could be lifted as a single unit. The lifting process required engineering ingenuity. Dietrich couldn't simply hoist 300 pounds of floor frame 8 feet into the air alone. He constructed a wooden crane, using a tripod of lodge pole pines and a pulley system with rope purchased at Fort Union. The crane stood 12 feet tall, positioned directly over the cantilever foundation. He attached ropes to the floor frame's corners and began the slow process of raising it. The work took 3 days. He would crank the pulley system to lift one corner 6 inches, then secure it with temporary supports. Then he'd lift the opposite corner to match. The frame rose incrementally, swaying and shifting with each adjustment. Twice the temporary support slipped, and the frame dropped several inches, nearly destroying hours of work. But gradually the floor frame rose to the correct height and settled onto the iron brackets mounted atop the angled support beams. Dietrich bolted the frame to the brackets using heavy iron pins that passed through both the brackets and the frame logs. The connections were permanent and rigid. With the floor frame secured, he laid the floorboards, split planks fitted tightly together and pegged to the joists beneath. For the first time, he had a working platform 8 feet above ground. He climbed onto it and stood at the center, testing for flex or movement. The platform held solid. Now came the walls. He had cut and prepared 40 logs for wall construction, each 12 feet long and 10 inches in diameter. Getting them onto the elevated platform required the same pulley system used for the floor frame, but now he was lifting individual logs and positioning them precisely for corner notching. He worked alone, spending entire days lifting a single log, positioning it, and securing it before starting the next. The walls rose slowly. By September, he had completed 3 courses, 18 inches of wall height. Wilhelm Brenner visited during this phase and watched Dietrich struggling to position a log on the elevated platform. "This is madness, Stoltzfus. You've spent 2 months on this. You could have built 3 regular cabins in that time." Dietrich didn't argue. He simply continued working. By late September, the cabin walls stood 6 feet tall, with 4 more courses needed to reach the roof line. Dietrich had worked through the technical challenges of elevated construction, but the chimney presented a problem that threatened the entire design. A functional stone fireplace and chimney could weigh 1,500 to 2,000 pounds. A massive point load concentrated on one corner of an elevated structure designed for distributed weight. Traditional chimneys were built from the ground up, with their own foundation independent of the cabin structure. But Dietrich's cabin floated 8 feet above ground. Building a separate chimney foundation would defeat the thermal isolation purpose. It would create a direct thermal bridge between ground and cabin. The chimney had to be integrated into the elevated structure, while somehow not exceeding the weight capacity of the cantilever support system. Dietrich spent 3 days calculating weight distribution options. He could reduce chimney mass by using thinner stones and less mortar, but that risked structural failure during thermal expansion and contraction cycles. He could position the chimney at the center of the cabin where support was strongest, but that would consume valuable interior space and complicate the floor plan. Or he could engineer a lighter chimney design using techniques he'd never attempted. He chose the third option. Instead of building a massive stone chimney from cabin floor to roof peak, he would create a hybrid system. The firebox and lower chimney section, the parts requiring greatest heat resistance, would use traditional fieldstone construction, but above the roofline, where heat was less intense, he would transition to a lighter design using thin stone veneer around a core structure of mortared clay and brick fragments. The work began with reinforcing the corner where the chimney would sit. He added extra floor joists beneath that section, distributing the chimney's weight across multiple support points rather than concentrating it at one location. Then he began gathering stones. Unlike his previous work with purchased materials, the stones were free but required enormous effort. He spent 2 weeks collecting field stones from a rocky hillside half a mile away, hauling them by hand and selecting each piece for size and shape. The firebox construction demanded precision. He built it slightly smaller than traditional designs, 30 inches wide rather than the typical 36, saving weight while maintaining adequate heating capacity. The back wall angled forward at the top, creating a smoke shelf that would reflect heat into the room and prevent downdrafts. Every stone was carefully positioned, with minimal mortar to reduce weight. As the chimney rose through the roofline, Dietrich began the transition to lighter construction. He built wooden forms and packed them with a mixture of clay, small stone fragments, and lime mortar. Once hardened, this composite material had adequate strength for the upper chimney while weighing 60% less than solid stone. He faced the exterior with thin stone veneer for weather protection and appearance. The chimney topped out at 4 feet above the roof peak in mid-October. Total construction time was 3 weeks. Final weight, by Dietrich's calculations, was approximately 1,100 pounds, still substantial, but within the support system's capacity. He lit a test fire and watched smoke draw properly up the flue and exit cleanly. The hybrid design worked. With walls and chimney complete, Dietrich turned his attention to interior details that would maximize the thermal advantage of elevation. The floor, the entire reason for this elaborate construction, required more than simple planking. He needed to create a barrier that would prevent any residual cold air from penetrating upward while maintaining structural integrity under daily use in furniture. Weight. The existing floorboards formed the structural layer, but Dietrich added a second floor above them. He laid down a layer of dried grass and moss 6 inches thick across the structural boards, packing it tightly into every gap. This organic insulation would trap air and create additional thermal resistance. Over the grass layer, he laid thin split planks, his finish floor, leaving small expansion gaps that he filled with a mixture of clay and pine pitch. The result was a double floor system with a 6-inch insulation layer sandwiched between structural and finish surfaces. Total floor thickness exceeded 8 inches, creating substantial thermal mass that would resist temperature changes. More importantly, the entire floor assembly floated 8 feet above frozen ground, with only the narrow contact points of the angled support beams connecting it to earth. Heat loss through those contact points would be negligible compared to conventional ground-level construction. Dietrich tested the floor's temperature properties using a simple experiment. He placed a metal plate on the floor overnight while maintaining a small fire in the fireplace. In morning, the plate's underside, touching the floor, registered 48 degrees. He repeated the test in Wilhelm Brenner's ground-level cabin. The plate registered 26 degrees. The 22-degree difference represented heat not being stolen by frozen earth, heat that would remain in the living space. He built sleeping platforms 18 inches above the finished floor, providing additional elevation and creating storage space beneath. The platforms were simple, split log frames with rope webbing to support bedding, but their elevation meant a person sleeping would be nearly 10 feet above ground level, positioned in the warmest air layer where heat naturally accumulated. Interior walls remained bare logs, but Dietrich applied clay chinking mixed with animal hair to seal gaps. The chinking wasn't primarily for thermal purposes. The elevated design already solved the major heat loss problem, but for wind protection and moisture control. Every gap sealed meant less air infiltration during storms. The cabin's interior measured 12 feet by 20 feet, 240 square feet of living space. Small by some standards, but adequate for a single trapper. The fireplace occupied one corner. The sleeping platform ran along the opposite wall. A work table, storage shelves, and trap preparation area filled the remaining space. Everything was overbuilt by frontier standards, thicker logs, more robust joinery, excessive reinforcement, but Dietrich had learned through Heinrich's death that frontier standards were inadequate. By late October, the interior was functionally complete. The cabin had taken 4 months of solo construction, 10 times longer than a conventional structure. Every trapper who saw it still considered it a bizarre experiment, but Dietrich knew the engineering was sound. He had created thermal isolation that no ground-level cabin could match. Winter would prove whether the time investment had been worthwhile. The elevated design created an unexpected advantage: defense and wildlife protection. A cabin 8 feet off the ground was effectively inaccessible to most threats without deliberate effort. Grizzly bears, wolves, and potential human attackers would find entry far more difficult than with ground-level structures. But this advantage created a new problem. Dietrich also needed reliable access. A permanent stairway would compromise security and provide easy access for anything that wanted to reach the cabin. Dietrich designed a removable ladder system instead. He constructed a ladder 12 feet long, using 2 pine poles as rails with wooden rungs mortised and pegged every 12 inches. The ladder was substantial enough to feel secure while climbing, but light enough for one man to lift and pull up after entering the cabin. He attached the ladder's top end to iron hooks mounted beside the door. When deployed, the ladder angled from ground to doorway at approximately 60 degrees, steep but climbable, while carrying supplies or firewood. When retracted, Dietrich would climb up, then pull the ladder inside and secure it horizontally along the interior wall. With the ladder removed, the cabin entrance sat 8 feet above ground with smooth log walls offering no handholds or footholds. The door itself was built to the same excessive standards as everything else in the structure. Thick planks reinforced with iron straps mounted on heavy hinges mortised into the doorframe. A wooden bar dropped into iron brackets secured it from inside. From outside, the door could only be opened by someone with the ladder and knowledge of how to operate the interior bar through a small, hidden slot. Windows presented similar considerations. Dietrich had cut 2 window openings during wall construction, each 18 inches square, positioned 5 feet above the interior floor. From outside, the windows sat 13 feet above ground, well beyond reach of bears or humans without climbing equipment. He built shutters from thick planks that could be barred from inside and covered the openings with oiled paper that admitted light while blocking wind. The elevated position provided unexpected visibility advantages. From inside, Dietrich could see 300 yards in every direction across the clearing he'd established. Anyone approaching would be visible long before they reached the cabin. At night, the elevation put him above the typical sight lines of wildlife moving through the area. He could observe without being observed, a reversal of the usual frontier dynamic where humans were always potentially prey. Security considerations extended to fire safety. An elevated wooden structure represented significant fire risk. If the cabin burned, occupants would be trapped 8 feet above ground. Dietrich addressed this by keeping the removable ladder near the door for emergency deployment. He also ensured the windows were large enough for emergency exit if necessary, though jumping 13 feet onto frozen ground would risk serious injury. The defensive advantages became apparent when a grizzly investigated the structure in early November. Dietrich watched from inside as the bear circled the elevated cabin, sniffing and testing. It reared on hind legs but couldn't reach the cabin floor. It pushed against the support beams but couldn't shift the solidly braced structure. After 20 minutes, it left. A ground-level cabin would have required armed defense. The elevated design made defense unnecessary. The first snow fell on November 3, 1837, light flurries that dusted the mountains and melted by afternoon. Dietrich moved his supplies into the completed cabin that evening, 4 months and 2 weeks after beginning construction. Everything he owned, traps, tools, food stores, ammunition, clothing, and Heinrich's few possessions he'd kept, fit comfortably in the interior space with room to spare. He lit the first functional fire in the stone fireplace and sat on his sleeping platform, watching flames consume split pine logs. The fire drew properly, with smoke exiting cleanly through the chimney and heat radiating into the room. Within an hour, the interior temperature had risen to comfortable levels. He removed his outer coat, something he'd rarely been able to do in his previous cabin, even with a roaring fire. The floor remained noticeably warmer than any cabin floor he'd experienced. Bare feet on the planking didn't produce the immediate cold shock typical of winter cabins. The double-layer floor system with its grass insulation was working. More significantly, the 8-foot elevation was interrupting thermal transfer to frozen ground. Heat, generated by the fireplace, stayed in the living space instead of bleeding away into the earth. Wilhelm Brenner visited the next morning to see the completed structure. He climbed the ladder, skeptically testing each rung before committing his weight, and entered the cabin with obvious reluctance, as if expecting the floor to collapse beneath him. He examined the interior, studying the fireplace construction, floor system, and overall craftsmanship. "Well, Stoltzfus, I'll admit it's built solid. Still think it's a waste of effort, though. We'll see how it holds up when real winter hits." Other trappers stopped by over the following weeks, curious about the strange, elevated cabin that had consumed Dietrich's entire construction season. Some were impressed by the quality of workmanship. Others remained skeptical. Otto Lindemann examined the cantilever support system with genuine interest, asking technical questions about load distribution and connection methods. But even Otto seemed doubtful about the thermal benefits. "I hope you're right about staying warm," he said. "Otherwise, you've spent 4 months building an expensive ice box in the sky." The mockery continued. Trappers referred to the structure as Stoltzfus's folly, or the floating cabin. Wilhelm Brenner told anyone who would listen that Dietrich had lost his mind after Heinrich's death and built a monument to grief rather than a functional shelter. Some questioned whether the elevation would make the cabin colder by exposing it to wind. Others predicted the structure would collapse under snow load. Dietrich didn't argue or defend his work. He simply prepared for winter, as he always had. Splitting firewood, organizing supplies, repairing traps and equipment. But this year, he split half as much wood as previous seasons. His calculations suggested the thermal efficiency of the elevated design would require far less fuel to maintain comfortable interior temperatures. If he was wrong, he'd frozen to death by February. If he was right, he would revolutionize mountain cabin construction. By mid-November, as temperatures dropped and serious winter weather approached, he would have his answer. The temperature dropped to -22 degrees on November 18th. Dietrich woke before dawn and added 2 logs to the fire that had burned down to coals overnight. Within 15 minutes, the interior temperature rose from 45 degrees to 62 degrees, a recovery rate that would have been impossible in his previous ground-level cabin. He dressed in moderate clothing and prepared breakfast while monitoring how the structure performed under genuine cold stress. The floor remained warm enough to walk barefoot without discomfort. He placed his hand on the floorboards near the exterior wall, the coldest location in any cabin, and felt only mild coolness rather than the bone-deep cold typical of ground-level construction. The thermometer mounted near the sleeping platform registered 58 degrees at floor level, 65 degrees at chest height, and 70 degrees near the ceiling. The temperature gradient was normal, but the absolute values were 15 to 20 degrees warmer than comparable measurements in conventional cabins under similar conditions. Most significantly, the fire required minimal feeding. Dietrich added one log every 2 hours throughout the day, maintaining comfortable warmth with less than half the fuel consumption of previous winters. By evening, he had burned through approximately 30 pounds of split wood, a quantity that would have barely maintained survivable temperatures in a ground-level cabin during negative 20-degree weather. He documented everything in his journal: exterior temperature, interior temperature at 3 heights, fire feeding schedule, wood consumption, and subjective comfort notes. The data would be meaningless to most trappers, but Dietrich understood its significance. The elevated design was performing exactly as his calculations had predicted. Heat generated inside the cabin was staying inside rather than conducting into frozen ground. Over the next 3 weeks, temperatures fluctuated between negative 10 and negative 30 degrees, typical early winter conditions. Dietrich continued monitoring and documentation. His daily wood consumption averaged 25 to 35 pounds depending on exterior temperature and wind conditions. In his previous cabin during comparable weather, he had burned 60 to 80 pounds daily and still endured cold interior conditions. Wilhelm Brenner stopped by in early December during a cold snap. The exterior temperature was negative 26 degrees. Wilhelm arrived bundled in every piece of clothing he owned, including a buffalo robe wrapped over his coat. He climbed the ladder and entered Dietrich's cabin, then stopped and stared. Dietrich sat at his work table in shirt sleeves, repairing a trap mechanism. A modest fire burned in the fireplace, nothing like the roaring blazes Wilhelm maintained in his own cabin just to stay alive. "How is it this warm in here?" Wilhelm asked, removing his outer layers. "My cabin is barely 40 degrees with a fire going all day. This feels comfortable." Dietrich explained the thermal isolation principle again, showing Wilhelm the floor construction and describing how elevation interrupted heat loss to frozen ground. Wilhelm examined the floor system, placing his hands on the planking and feeling the retained warmth. His skepticism wavered. "This actually works. You weren't crazy. This actually works." Word began spreading through the trapping community. Stoltzfus's elevated cabin wasn't just an eccentric experiment. It was demonstrably warmer and more fuel-efficient than conventional construction. Some trappers remained skeptical, attributing the performance to the specific location or superior fireplace design rather than elevation. But others began asking questions about construction methods and engineering principles. December brought weather that tested every structure in the northern Rockies. Temperatures plunged to negative 40 degrees and stayed there for 2 weeks. Snow fell continuously, accumulating 3 feet on level ground and drifting to 6 feet in protected areas. Winds exceeded 40 miles per hour during storms, driving snow horizontally and creating wind chills approaching negative 70 degrees. Men who had survived a decade in the mountains began questioning whether they would survive this winter. Wilhelm Brenner's cabin, built using standard construction methods on level ground near the creek, became uninhabitable. Despite burning through 3 cords of firewood per week, Wilhelm couldn't keep the interior temperature above freezing. Ice formed on the interior walls. Water buckets froze solid within hours. His sleeping furs became stiff with accumulated frost. He wore every piece of clothing he owned to bed and still woke shivering. The problem was identical to what had killed Heinrich Vogel. Wilhelm's cabin floor sat directly on frozen earth. The ground beneath had frozen to a depth of 3 feet, creating a massive thermal sink that drew heat downward faster than his fireplace could generate it. The fire heated the upper cabin adequately, but at floor level, where Wilhelm slept and spent most of his time, temperatures remained near or below freezing, regardless of how much wood he burned. On December 19th, Wilhelm abandoned his cabin. He packed essential supplies and moved 5 miles east to stay with Otto Lindemann, whose cabin was slightly better insulated and offered the survival advantage of shared body heat and combined firewood resources. Wilhelm's cabin sat empty, its fireplace cold, interior temperature dropping to match exterior conditions. When he returned in spring, he would find frozen food stores, ruined supplies, and evidence that the structure had been investigated by a bear that had torn through the door and ransacked the interior. Other trappers faced similar crises. A man named Jacob Weiss lost 3 toes to frostbite, despite never leaving his cabin during the coldest week. His cabin's floor temperature dropped so low that prolonged sitting allowed cold to penetrate through clothing and boots, causing tissue damage without his immediate awareness. Another trapper, Ernst Mueller, burned through his entire winter firewood supply by mid-January and was forced to travel to Fort Union early to purchase more, a dangerous journey in extreme cold that nearly killed him when his horse broke through ice on a frozen river. Dietrich's elevated cabin performed flawlessly throughout the temperature extremes. His daily firewood consumption increased to 40 pounds during the coldest period, still half what conventional cabins required. Interior temperatures remained comfortable. He never wore his heavy buffalo robe indoors. His feet stayed warm, his water bucket never froze. He slept soundly without layering every fur he owned. The contrast became obvious to anyone who visited. Otto Lindemann brought Wilhelm to Dietrich's cabin during the worst of the cold snap. Both men were exhausted from weeks of struggling to stay warm. They entered Dietrich's cabin and immediately felt the difference. The interior was genuinely warm, not just survivable, but comfortable. Wilhelm sat on the floor and placed his bare hands on the planking. "My cabin floor is so cold it burns your skin. This feels normal, like a floor should feel." Dietrich shared his documentation, temperature records, fuel consumption data, construction details. Otto studied the information with genuine interest while Wilhelm stared at the fireplace, watching the modest fire that was keeping the cabin comfortable. "I burned 6 times this much wood yesterday and still froze," Wilhelm said quietly. "You were right, Stoltzfus. We've been building wrong for generations." January 14, 1838 began with temperatures at negative 48 degrees and falling. By evening, it had reached negative 56 degrees, the coldest night recorded in the region in 20 years. Otto Lindemann maintained a massive fire in his cabin 7 miles from Dietrich's location. Wilhelm Brenner, still staying with Otto after abandoning his own cabin, fed logs continuously into the flames. Despite their efforts, the interior temperature hovered near 35 degrees. Frost accumulated on interior walls. Their breath crystallized instantly in the air. Around midnight, disaster struck. A log rolled out of the fireplace onto the plank floor. Otto and Wilhelm were both asleep, exhausted from weeks of cold weather survival. The log smoldered against the dry planking, generating smoke and heat. Within minutes, the floor ignited. Flames spread rapidly across pitch-soaked wood that had been dried by months of fireplace heat. Otto woke to smoke filling the cabin and flames consuming the floor near the fireplace. He shouted to Wilhelm, and both men grabbed what they could, coats, boots, a blanket, and fled into the night. They had perhaps 90 seconds from waking to evacuation. Everything else, supplies, furs, weapons, tools, was left behind as flames engulfed the interior. They stood 50 yards away in negative 56-degree weather and watched Otto's cabin burn. The structure, dried by winter heating and filled with flammable materials, was completely involved within 10 minutes. They faced immediate crisis. 2 men in partially fastened clothing, 1 blanket between them, 7 miles from the nearest shelter, in temperature cold enough to kill within hours. Otto knew the area's geography. Dietrich's elevated cabin was closer than any other occupied structure. They began walking, moving as quickly as possible through knee-deep snow, knowing that stopping meant death. The journey took nearly 2 hours. Both men were approaching hypothermia when they saw lamplight through Dietrich's cabin windows. Otto shouted, his voice barely carrying through the cold air. Dietrich heard, lowered the ladder, and helped both men climb into the cabin. They collapsed inside, shaking uncontrollably, their exposed skin showing white patches of frostbite. Dietrich acted immediately. He moved them away from the fireplace. Rapid rewarming of frozen tissue causes severe damage, and wrapped them in furs. He prepared warm liquid, not hot, and made them drink slowly. He examined their frostbite injuries, assessing severity and applying basic frontier treatment. Wilhelm had significant damage to his fingers. Otto's face showed frozen patches that would likely scar. But both men were alive. They remained in Dietrich's cabin for 3 days while the temperature gradually moderated. The elevated structure easily accommodated 3 occupants. The thermal efficiency meant even with 3 men, additional body heat and increased door openings for sanitation needs, the cabin remained comfortable with only modest increases in firewood consumption. Wilhelm and Otto recovered slowly, treating their injuries and processing the trauma of nearly dying. On the 3rd day, Wilhelm spoke what both men were thinking. If your cabin hadn't existed, we'd be frozen corpses in the snow. This design, this elevation, it saved our lives. Otto nodded agreement. I need to understand how you built this. When spring comes, I'm rebuilding my cabin using your methods. Dietrich shared everything: drawings, measurements, construction techniques, engineering principles. He held nothing back. The knowledge had saved 2 lives. If it could save more, that was reason enough to spread it freely. Spring 1838 arrived late and reluctant, with snow lingering into May and temperatures remaining below freezing most nights. As trappers emerged from their winter shelters and assessed damage, the contrast between Dietrich's elevated cabin and conventional structures became impossible to ignore. Dietrich had survived the harshest winter in 2 decades comfortably, using half the firewood of any other trapper. Otto and Wilhelm had survived only because Dietrich's cabin existed when they needed refuge. Those facts spread through the scattered mountain community faster than any previous news. Men who had mocked Stoltzfus's folly 6 months earlier now asked to examine the construction. Dietrich welcomed visitors, explaining the thermal isolation principle and demonstrating the cantilever support system. He showed them his temperature documentation and firewood consumption records. The data was undeniable. Elevation eliminated the primary heat loss mechanism that made mountain winters deadly. Jakob Weiss, who had lost 3 toes to frostbite, spent 2 days studying every aspect of the structure. He measured the support beam dimensions, examined the connection methods, and calculated the geometric angles of the cantilever system. I can't afford iron brackets, he told Dietrich. Can this work with wooden connections? Dietrich explained that wood connections would require larger timbers and more complex joinery, but yes, the principle would work. The critical element was elevation and thermal isolation, not the specific materials. Ernst Müller asked about adapting the design for a larger cabin to accommodate his family. Dietrich worked through the mathematics with him. A larger structure would require proportionally heavier support beams and possibly additional support points, but the engineering principles scaled. Müller would need to transport larger timbers from Fort Union or find suitable trees locally, but an elevated family cabin was achievable. Wilhelm Brenner, whose cabin sat abandoned and bear-damaged, announced he would rebuild using elevated construction. He asked Dietrich to help with the initial engineering, calculating support requirements, and designing the foundation system. Dietrich agreed, with one condition: Wilhelm would share the knowledge with anyone who asked. The techniques shouldn't be secret or proprietary. They should spread freely to anyone who needed them. Wilhelm agreed. Otto Lindemann had already begun preparing for reconstruction. His cabin was destroyed, which meant he needed to rebuild anyway. He purchased heavy timbers at Fort Union in June and transported them to his burned cabin site. Dietrich traveled to Otto's location and spent a week helping establish the foundation system, setting stone piers, positioning the primary support beam, and raising the floor frame. Otto would complete the walls and roof himself, but Dietrich ensured the critical elements, elevation and support geometry, were executed correctly. By late summer 1838, 3 elevated cabins were under construction in the northern Rockies territory. Otto's was most advanced, with walls at full height. Wilhelm's foundation was complete and floor frame mounted. Jakob Weiss had begun site preparation and timber collection. None would be finished before the following winter, but all 3 men understood they were building structures that would keep them alive during future temperature extremes. The phrase Bridger-style cabin had emerged from Samuel Bridger's innovations decades earlier, but now a new term appeared: elevated cabin, or sometimes Stoltzfus construction. The names were less important than the principle. Men were learning that survival didn't require suffering through cold, burning, excessive firewood and accepting frostbite as inevitable. It required building better. Over the next 5 years, elevated cabin construction spread throughout the northern Rocky Mountain trapping territories. The technique evolved as different builders adapted core principles to local conditions and available materials. Some trappers used vertical post systems instead of cantilever designs when suitable timber was unavailable. Others incorporated stone pier foundations of varying heights based on terrain and drainage requirements. But every variation maintained the essential element: significant air gap between cabin floor and frozen ground. By 1842, an estimated 30 to 40 elevated cabins existed across Montana, Wyoming, and northern Idaho territories. The exact number was impossible to determine given the scattered, isolated nature of mountain settlements, but references in trading post records and trapper correspondence confirmed widespread adoption. Men who built elevated structures reported identical experiences: drastically reduced firewood consumption, warmer interior temperatures, and elimination of the floor-level cold zones that had killed Heinrich Vogel and threatened countless others. The technique's reputation spread beyond the trapping community. When homesteaders began moving into mountain valleys in the early 1840s, some encountered abandoned elevated cabins and recognized their superior construction. Several homesteading families occupied and maintained structures originally built by trappers, benefiting from engineering that predated their arrival by years. The elevated design proved particularly valuable for families with small children, who were most vulnerable to cold-related illness and injury. Military expeditions mapping Western territories documented elevated cabins in their reports. An 1843 Army survey of the Yellowstone region specifically noted cabins of unusual construction, elevated on timber supports, reportedly built to prevent heat loss during extreme winter conditions. The surveyors recognized the engineering sophistication, though they incorrectly attributed the innovation to French-Canadian trappers rather than to Dietrich Stoltzfus specifically. The economic impact was substantial for individual trappers. Reduced firewood requirements meant less time spent on fuel gathering and more time running trap lines. A trapper using an elevated cabin could work a larger territory with the same time investment, increasing fur harvest and annual income. The efficiency advantage was significant enough that some trappers built elevated structures despite the additional construction time, viewing it as investment that paid returns every winter. Technical refinements emerged through collective experience. Trappers discovered that positioning the primary support beam perpendicular to prevailing winds reduced structural stress during storms. They learned that stone piers needed to extend below frost line to prevent heaving that could destabilize the foundation. They developed improved connection methods using wooden pins and rawhide lashings when iron hardware was unavailable. Each refinement was shared informally through the network of mountain men who crossed paths at trading posts and along trap lines. Not every trapper adopted elevated construction. Some remained skeptical despite documented evidence. Others lacked the carpentry skills or resources for complex building projects. Traditional ground-level cabins continued being built throughout the 1840s, particularly by transient trappers who didn't plan to occupy structures for multiple seasons. But for men committed to long-term mountain residence, elevated construction became the recognized superior method. The question wasn't whether elevation worked. 5 years of field testing had proven that, but whether individual builders had the skill and resources to execute it properly. Dietrich Stoltzfus left the mountains in spring 1844. The fur trade had collapsed as beaver populations declined and eastern markets shifted to silk for hat production. At 39 years old, he had spent 11 years in the wilderness and saved enough money to start a different life. He sold his traps and equipment, packed his personal belongings, and rode east toward settlements along the Missouri River, leaving his elevated cabin fully furnished and weather-tight. He settled in a small farming community in eastern Montana Territory, purchasing 40 acres and building a modest frame house using conventional construction methods. The elevation techniques he had pioneered were unnecessary at lower altitude with milder winters. He married in 1846 a widow named Anna Krieger, who had lost her husband to cholera during westward migration. They had 2 children over the next 4 years. Dietrich worked his farm, participated in community life, and rarely spoke about his trapping years or the cabin he had built. His elevated cabin remained standing in the mountains, maintained by occasional occupants who recognized its value. In 1848, a prospector named Thomas Callahan discovered it while exploring the region and used it as base camp for an entire winter. Callahan's journal entries described the structure's warmth and efficiency, noting that it was the finest winter shelter in the territory, built by someone who understood cold. In 1852, a homesteading family occupied it for 3 years while establishing their ranch. The cabin's thermal performance allowed them to survive winters that killed livestock and drove less prepared settlers back to lower elevations. The structure's longevity proved another advantage of elevated construction. Ground contact cabins typically required major repairs within 5 to 7 years as foundation logs rotted from moisture exposure. Dietrich's elevated design eliminated ground moisture problems entirely. The support beams showed minimal deterioration even after 15 years. The cabin remained structurally sound and fully functional, requiring only routine maintenance of chinking and roof repairs. By the 1860s, when mining operations brought larger populations to Montana Territory, variations of elevated cabin design had become standard for high-altitude winter construction. Mining companies built elevated structures for their workers. Trading posts in mountain locations used elevation to protect valuable goods from ground moisture and maintain warmer storage conditions. The technique Dietrich had developed in response to his partner's death had evolved into accepted frontier architecture for cold climate construction. Dietrich Stoltzfus died in 1871 at age 66, never knowing how far his innovation had spread or how many lives it had saved. He was buried in a small cemetery near his farm, his gravestone identifying him simply as a farmer and family man. His children knew he had been a trapper, but nothing about elevated cabins or thermal engineering. His original cabin stood until 1883, when it was finally dismantled by a rancher who needed the timber for fence construction. By then, it had sheltered humans for 46 years, 6 times longer than typical frontier cabins lasted. The rancher, examining the Cantilever foundation system before dismantling it, reportedly said it was the finest carpentry he'd ever seen from the trapping era. The timbers, even after decades of exposure, remained sound enough for reuse in new construction.